We used it before this semester, right? And I told you that gives you cosine plus I times sine, right? Euler's formula. Here's another way you could have discovered that. If you hadn't known this before, but you knew that the exponential was this given by this power series, right? How does the number I behave? I squared is what? Minus 1. What's I cubed? Minus I. I to the 4th. 1. I to the 5th. I to the 6th. Minus 1. I to the 7th. Negative I to the 8th. Okay, you're going to get bored of this pretty soon, I hope. But and so forth, right? So as you study powers of the imaginary number, you either have plus or minus 1 or plus or minus I. There's these 4 cases, right? So if you plug in Ix into the power series for the exponential, you get 1 plus Ix squared plus Ix cubed over 3 factorial plus Ix to the 4th over 4 factorial plus Ix to the 5th over 5 factorial, right? This pops out an I. That gives me like a minus I, right? This gives me minus I cubed. This gives me a 1. This gives me an I again, right? So if we just regroup those terms, we've got 1 minus 1/2 x squared plus 1 over 4 factorial x to the 4th plus dot, 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 dot. That's the real terms. Plus I times x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th plus dot, dot, dot. Those are the odd terms. This thing that I just did double underline in green is exactly the Maclaurin series for sine of x. That is what it is. That's what I wrote earlier under the projector screen when we were looking at its first 9 Maclaurin, first 9 Taylor polynomials centered at 0, right? It's exactly the formula I mentioned. And you can see that this has to match cosine, and that has to match sine, just comparing the real and the imaginary coefficients. Now, if you don't like this way of thinking about it, of course, you can go back and be boring and calculate the arbitrary derivative of cosine and arbitrary derivative of sine and plug in 0 and derive the same formulas, right? Just to be clear, let me write them down for our future reference. Cosine of x is equal to the sum j equals 0 to infinity minus 1 to the j over 2j factorial x to the 2j. And sine of x is equal to the sum j equals 0 to infinity minus 1 to the j over 2j plus 1 factorial x to the 2j plus 1. So there you go. And I usually, just for the sake of completeness, write the first 2 terms. This is like 1 minus 1/2 x squared. And this is x minus 1 over 6 x cubed. Sometimes I'll write the first 3 terms if I'm feeling more generous and have more board space. But do those look like anything else we've seen today? It's nearly the same except for what? Minus 1. And sinh, same except for minus 1. If I ask you a question about approximation, which is the friendlier question to ask you about? Sine or sinh? Cosh or cosine? Incorrect. Why? What is our beloved most simple approximation theorem? The alternating series estimation theorem, which says that for an alternating series, the next term is a bound on the error in the partial sum, right? Now, Mr. An, you can redeem yourself by saying, I was talking about sinh of minus 1. I'm like, oh, okay, sinh of minus 1. I gotcha. See, because sinh of minus 1 would be like minus 1 plus 1 over 3 factorial minus 1 over 5 factorial plus 1 over 7 factorial. And then you'd be like, see, it's alternating. You are just being naive and thinking only of positive x's. That's true. That's true. So there you go. I have redeemed your comment. In the case we were looking at a negative x, sinh would be the easier question. But for positive x, then sine and cosine are alternating, right? Sorry, I shouldn't pick on Mr. On. Let's see here. It's fun. Let's see here. I should get to know more of you better so I could pick on you more effectively. Let's see here. You don't seem scared enough. Let me show you another example. Where my watch? Where is my... No. I will eventually find my cell phone. Otherwise, I'm going to... Uh-oh. Where on earth did I put my phone? Did you guys see my phone? By the way, is the audio still working? My batteries are a little bit suspect earlier. Okay. Did any of you guys see my phone anywhere? Don't be so happy. All right. Now, so up here is another example. If you wanted to find the Maclaurin series for like x cubed times sine of x squared, we can again use the substitution idea. Just plug in x squared in the place of basically x for the sine. Like, you can erase x here, right? And sometimes I think it's helpful for students to, instead of putting x here, put u here, because so often that's how we want to use it. We want to use it as a substitutionary template, as opposed to actually having an x there. So it might be helpful for you to write things again with u's, just so you can think, okay, so I'm just plugging in this case, x squared. And so like there's the power series for x cubed times sine of x squared. To get from here to here, notice that like 2 times 2j plus 1 is 4j plus 2, but then we have to add 3 from the x cubed multiplied out here, right? So like I'm just plugging in x squared into the sine series, and then I bring in the x cubed that adds 3 to the exponent. And there you go, that's the Maclaurin series for x cubed times sine of x squared. Again, I would advise against using the direct Taylor series generation formula. That would not be the wise way to calculate this. You want to use what you know. What do we know? Sine, exponential, cosh, sinh, and cosine. At the moment, those are the ones we know. Hey, we also know geometric series, though, right? Let's take the remaining 5 minutes of class or so and just think harder about geometric series. What can we do with geometric series? I will at some point feel guilty about not telling you theory and stuff, and I will have to go back and we'll have to cover how to figure out the domain of these things and so forth and so on. That will happen, but I'm gonna, as long as I can get away with here, I'm gonna just keep showing you how to calculate for a while. Once we're done with how to calculate, once I have shown you all of my various nefarious tricks for calculating power series, only then will I go back to the book and dot my T's and cross my I's or whatever it is. And so here we go. Geometric series tricks. Start out small. F of x is 1 over 1 plus x squared. I have till 11, right? Yeah, okay. So this is the sum, k equals 0 to infinity, of minus x squared to the k power y. A equals to 1, r is equal to minus x squared, right? Geometric. Something really weird about this example, by the way. So there you go. There's the power series for 1 over 1 plus x squared. What's its domain? this, what I've just underlined, is this is only for what? For x squared minus x squared less than 1, aka the absolute value of x less than 1, right? In other words, this is good for minus 1 to 1. It was understandable why we had trouble at 1 for the thing I just erased, right? There was a vertical asymptote at 1. What's the deal with this function, though? What does 1 over 1 plus x squared look like? It's not a troublemaker. It's just this guy. Right? This is y equals 1 over 1 plus x squared, right? Why on earth is it that the power series only approximates it like that much? What's stopping it from going further? It's weird, isn't it? Just point it out. It's one of the fundamental mysteries of real calculus. What happens if you integrate this term by term? Or let's think about it this way. The integral of dx over 1 plus x squared is what? Well, that's inverse tangent of x, right? You guys know that. But that's also equal to the integral of the sum, k equals 0 to infinity of minus 1 to the k, x to the 2k, right? dx. So by the term-by-term integration theorem, I get a constant plus the sum, k equals 0 to infinity of minus 1 to the k, divided by 2k plus 1, x to the 2k plus 1. How do you figure out the constant? I mean, inverse tangent's a function, right? I guess this would also be plus a constant, fine, plus c1, right? So maybe this, so basically we see inverse tangent has to be equal to this series plus some constant, right? If you plug in 0, right? Plug in x equals to 0, we can get that c1 is equal to c, so that implies that inverse tangent of x is just equal to what? That sum. In other words, inverse tangent of x is simply equal to x, Yeah, oh, sorry. K starts at 0. So x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th, and so forth and so on. There you go. There's a power series for inverse tangent. However, I arrived at this power series through rather indirect reasoning, didn't I? So, oh, my time's up. Thanks, guys. Oh, yeah, yeah.